going to spend the next couple of days talking about modeling with exponential functions. The general equation of an exponential function is y equals a b to the x, and you can have some kind of shifts. So, for example, you can have y equals a times b to the x minus c plus d. So there can be some shifts involved, but this is the general form. As long as um, as long as a and b are both non-zero. So you can't have either of these be zero. Neither of them could be zero, basically. So when we're looking at this, x is zero means that we have time is zero or whatever we're using as the variable is zero. That makes a the initial value. Okay. So a is the initial value there. So remember, when x is zero, b to the zero would make that one. So when x is zero, y equals a. And that means that a is the initial value or initial condition or what's happening at the beginning. Okay. And then b is the growth factor. So if b is greater than 1, that means we have exponential growth. The function is going to start slow and then grow like a typical exponent function. If b is less than 1, we have what is called exponential decay. So our graph starts like any normal exponential function and then starts to go down pretty fast. So we have exponential growth and we have exponential decay as our two options. B equals 1 is kind of a useless case because then you have 1 to the x power. You just have the line y equals a all the time. So that's kind of a useless case. So we really only talk about when b is greater than 1 or when b is less than 1. And when we say b is less than 1, b also has to be greater than 0, because if b is less than 0, that's pretty crazy. If you have a question about what that looks like, you can ask about it in class, or you can just explore it on Desmos. But if b is less than 0, then you have something like a times -2 to the x, and that would be pretty nuts. So we also, uh, remember, we have y equals a times b to the x. We can replace b with 1 plus or minus r. So instead of having b, we can see 1 plus or minus r instead. And essentially what that's doing is it's describing the rate that a function is growing or decaying. So if the rate of growth is, let's say, 10% growth, then r would equal 0.1. And you'd have 1 plus 0.1. And so that would mean b would be 1.1 in that case. If the rate of decay, let's say instead of growth, it is decay, then it would be 1 minus 0.1. So b in that case would be 0.9. Now notice that both of these meet exactly the same criteria that we talked about here. So when the growth rate was positive, or there was a growth rate, then b ends up being bigger than 1. If there was a decay or a decay rate, then b ends up being less than 1. So that is pretty straightforward. So here's two examples. In this case, the 10 represents the initial condition, the initial amount. And then we have this 0.4. Now 0.4 represents b. I can rewrite that as 1 minus 0.6. So my rate is a 60% decay in this problem. And this picture represents this graph. So as I look at this, notice that my window is shown. So this would be the point 0, 10. And then my decay rate is pretty fast. By the time we get down to to x is 2, the y value is very small. The y value looks like it's around 1 or 2. So it decreases pretty fast. And the x scale, notice, is 1. So it's going at a pretty fast rate of decay. Now, if I have y equals 2 times 1.015 to the x, 2 is the initial amount. And then notice my b is 1.015. So that's the same thing as 1 plus 0.015, which is a 1.5% growth. So that's my R. My R is 0.015 or 1.5%. So what I'm looking at is I know the point 0.02 is on the graph. And then as I continue to move up, notice that this window is very spread out. Like the X's go up by 10 and the Y's are going up by 1. So if I just look at, let's say, Y equals 5, the X is at 10, 20, 30, 40, 50, 60, somewhere between 60 and 70. So let's just say it's about 65, 65-ish, comma 5. So what we're looking at is a very slow growth rate, which makes sense because the growth is about 1.5%. So that's kind of what that looks like. A couple example word problems. Most of the time, you will be able to use your calculator on these things. But here's just an example. So half-life of Advil is represented by R equals M times 0.5 to the T over 2. M is the initial dosage, and R is the amount of Advil remaining in the body, and T is the time in hours. So if you take a 200 milligram dosage, that means M is the initial dosage of 200, and then we have 0.5 to the 5 halves. That will equal R. So that's basically what we want. Now, why did I get 5 halves? Because T has to equal 5, because if you take the pill at 1 o'clock, 6 o'clock would be 5 hours later. So I would just type that in the calculator, and I end up getting 35.355. So there would be 35.355 milligrams left at 6 o'clock. Your new computer costs $1,500, but it depreciates in value by about 18% each year. So that means I will have the amount left, which is Y, is equal to the initial amount, 1,500, times 1 minus 0.18 to the X, because my rate is 18% and it's depreciating. So that means my B in total is going to be less than 1. So I can rewrite this as Y equals 1,500. I shouldn't put another equal sign here. Y equals 1,500 times 0.82 to the X. How much will my computer be worth in 6 years? 1,500 times 0.82 to the 6. I can type that in the calculator and end up getting $456.01. So $456.01 will be about how much my computer is worth in 6 years. Notice that this is an about. It's not going to give you an exact amount, but it's approximately how much it's depreciating each year. And then part C, how long will it take for your computer to be worth close to $0? It will never equal 0, because you can't have 0 equals a number times a positive number to an exponent. Like, this is never going to end up equaling 0. There's no way I can plug in anything for x to equal 0. But close to 0, let's just say $1. That's pretty close to 0, considering that the new computer cost $1,500. So now what I'm going to do is I'll solve this by hand. 1 over 1,500 equals 0.82 to the x. Then in order to get rid of an exponent, I can do log of both sides. So this will be log of 0.82, log base 0.82 of 1 over 1,500 equals x. So if I'm assuming that $1 is close enough to 0, then this will be what I type in the calculator, and I'll get an answer. So I type that in the calculator and I get about 36.852 years will be when it's equal to $1. So after that many years, the computer is equal to $1. And then I showed another way you can do it. You can actually graph y1 in your calculator is 1500 times 0.82 to the x, and y2 in your calculator is whatever the dollar amount it is. Now I put $1 as close enough to zero in this problem, but you can kind of figure out where it goes from there. So after about 36.852 years, it's about $1, which is pretty close to $0.